participants. And so some participants are only online. And so Sridhar is a professor at the University of North Carolina, Chapel Hill, who's a co-PI with us on a Scenic related project. And so he will tell us a little bit for what his group has been doing with Scenic. Right, Sridhar?
Yeah. So you can see the slides, right? Yeah. I would have loved to attend the session in person, but unfortunately, due to some personal reasons, I couldn't be there. But let's talk about automated test case generation using Scenic. And I think maybe some of you might feel this as slightly repetitive. So very quickly, again, one of the biggest challenge problems in recent days is to again, we have had prototypes of autonomous vehicles for close to 10 to 14 years now, but rather the biggest challenge right now is to make them reliable, and not just reliable in general, but reliable in a wide variety of contexts. So just to give you the scale of the different contexts in which autonomous vehicles operate, I'll start with a smaller question. So Google has right now claimed that its Waymo taxi service has driven for 200 million miles. But can you guess how many million miles do people in the US drive every year? Make a random guess. It's half a light year. So every year, the people in the United States are driving half a light year distance, right? It's literally an astronomical number, right? Again, can we enumerate all the scenarios that we see? Probably not, but at least what we want to do is to have some sort of coverage or thinking systematically about exploring all these scenarios in a systematic way, right? So what I will present is, so we started on this project more than 2 years ago, and we toyed with various simulation engines. And I'll tell you probably why Scenic is what you eventually converge to, right? So again, Waymo has claimed that it has driven 200 million miles, but technically all of these are nothing in comparison to the different scenarios that people see outside. Again, one recent incident that some of you may have familiarity with is that a bunch of autonomous vehicles, I think GM is the main culprit here. So in Austin, GM has several test vehicles, and apparently all these test vehicles were trying to pass through an intersection, and suddenly that caused a traffic jam. And you see that within the sequence of 3 cars, there's a poor fellow in an SUV stuck there, where now the driver is at the mercy of what these autonomous vehicles will do. Again, one of the reasons why we adopted Scenic is that you don't have access to these AVs in general testing scenarios. So you have limited access to these autonomous vehicles. And as Sanjit was just explaining, it is very tricky to choreograph some of these scenarios. Again, you want to generate scenarios that you may see in the wild, or you have some systematic way of enumerating them. But to choreograph these scenarios requires a lot of effort in setting up an environment somewhere and doing everything, right? And again, if you want to test an intersection at Austin, good luck trying to say that, okay, we have blocked off these intersections so that we can actually test in this. Not going to happen, right? And finally, a more underlooked part is the red tape, right? Imagine all the insurance premiums that you have to pay to test these. So the next best thing is to do in a simulation environment like Carla. And we actually tried it for a year and eventually gave up because of several reasons. So one is that whenever anyone uses simulation environment, there's a lot of boilerplate code involved. That is, for setting up an environment in Carla, again, it's not Carla's fault. It's trying to generate a simulation as faithfully as possible. So in a scenario, there are lots of other interesting aspects, like what is the road geometry, etc., etc. And if your main goal is to generate a new scenario, that entire difficulty is not capsulated at one place. The nice thing about Scenic is that it distills all this complexity about the relative positions and velocities of vehicles and lane descriptions and all that, and puts it in a place where you can actually do it. Whereas in regular Carla, this is distributed as some parameters and some scripts. And finally, the most important thing, which is why Scenic is probably very useful, is the lack of portability. So yeah, sure, you can generate scenarios in Carla, but what if the auto manufacturer says, no, Carla is like very naive. We have a much better photorealistic environment. Can you port your entire thing there? Right? Good luck trying to remove away all the parameters that are inbuilt in your test scenario and porting that entire thing to a new simulation agent. And we basically came to Scenic specifically for these reasons. It is simulator agnostic. It has a nice way to represent the scenarios, almost no boilerplate code, and code difficulty of scenario is encapsulated easily. So what I want to show you is in the brief time that I have to highlight a specific scenario or a specific way of generating scenarios. So you have seen where you provide a specification, and the scenarios that Verify tries to generate is to falsify the specification or that move it closer to near failure. But what we have attempted is to generate test cases of increasing complexity, and we have given a definition for a complexity. So the starting point is that we all want the vehicles to follow traffic rules, more or less, right? Again, the less part is likely up to debate. But if you want to formalize some sort of traffic rules, or if you want your vehicles to behave traffic rules, the first step that we did is to take these traffic rules that are provided in English into some sort of logical formulation. And for that, we picked, again, intersections are one of the most common places where a lot of autonomous vehicle accidents happen. So we picked, say, a typical rule like a yield to the right of way rule, which says that a vehicle should yield the right of way to all vehicles that have entered the intersection before. Right, and you can represent these in a first order logic sentence where you say, "Oh, I have two cars, say C1 and C2, and if C2 has arrived before C1, then C1 should yield to C2." Right. And here we had a quantifier saying that for all cars C1 and C2, and now you have a predicate which says arrived before is a predicate which can be evaluated to true or false given the trajectories of two vehicles, and yield to is another predicate that can be evaluated given the behavior of two vehicles, right? So this way you can write sentences in first order logic for these rules, and what we wanted to show or we wanted to try is to generate scenarios where we try to break some of these traffic rules. That is, we want the vehicles to violate some traffic rules, right? And so we picked some of the main traffic rules. Again, the number of rules is not necessarily important. If you most of the rules for, say, four-way stops can be summarized in 30 to 40 lines of these first order logic sentences. And our goal was to generate scenarios that make the situation increasingly difficult. So here is an example of a scenario that we have. So here is a four-way intersection where all the vehicles that come to the intersection has to first stop, then check for all the precedence rules and the right-of-way rules, and then enter the intersection according to what the traffic rule is according to them, right? And now what we want to do is to make these scenarios more and more difficult. And we define difficulty as follows. So say you have a scenario where a particular autonomous vehicle has behaved in a certain way. We want to reduce the space of possible behavior. So what we do is we introduce a new autonomous vehicle into the same intersection such that the previous behavior of autonomous vehicles becomes an invalid behavior. So our goal is to generate test cases that are more and more difficult. Right? So here is an overview of how we do it. again, I don't expect you to understand all these things at one position, but say there are some things that are given as input. So the scenario generation algorithm takes as input the current configuration, which is what are the lanes, what are the stop signs, etc., etc. And this part is still not yet fully automated. So you have to specify what are the traffic rules that you want to satisfy. And then you can either give a traffic scenario or you can generate one that you get from Scenic by generating some parameters. And then what our goal is to generate a new traffic scenario, and we give two additional things, which is called a complexity certificate, which tells you that this new scenario is more difficult than the previous scenario. And we also give a feasibility certificate, which means that this new traffic scenario is not impossible. That is, you cannot have, say, for example, two vehicles which are not the autonomous vehicle come into an intersection and block the intersection, in which case it's impossible for the autonomous vehicle to go through the intersection, right? So you have a feasibility certificate and a complexity certificate. So let me show you a brief illustration of this. So again, there might be this is a lot of animations at one go, so don't be scared. But I'll walk you through these in one after the other. So the first, look at the leftmost figure, right? So in the leftmost figure, we have an autonomous vehicle that's joining in from the south, and it waits for the first car to go through the intersection, as in to clear its path, and then completes the turn to the left, right? Or rather the west, right? So again, I'm using the cardinal direction as top as north, bottom as south, east and west. So again, you can see that ideally in scenario 2, we have increased or we have added one more non-ego vehicle, and the additional non-ego vehicle here is coming in from the east, and ideally the velocities and the position of this is generated automatically, so that the previous behavior would actually be illegal, right? But you see that these two are almost identical, and in fact, in this scenario, in scenario 2, this vehicle has violated the right of way of the car that is entering from the east. Why? Because the car that is entering from the east has entered the intersection before this, the vehicle should have waited for it to completely pass to the intersection, right? However, it did not, and we can progressively make it more and more difficult, right? Here is another illustration, right? I think in the interest of time, I'll skip the second illustration. This is a slightly more conservative approach. So this is called responsibility, safety, sensibility, safety agent, where the quote unquote, the high level principles of this have been formally verified. And it turns out that, this, even this one, if you look at the last one, it actually violates the safety and actually collides with one of these incoming vehicles. So again, if you think that, well, I started with a lofty goal of generating half a test cases for half a light year distance, well, we have again, scalability is the biggest challenge, and for that I have some interesting, exciting announcements for Scenic. One of them is that we have modified the current framework to actually use fuzzing as well. And one of the biggest new innovations is in porting the Scenic environment into a singularity environment. For those who are not familiar with, I think most of you are familiar with Docker environment. Singularity is a similar container environment that is much more used in academia. So this enables the deployment of clusters. And again, this is all work in progress, but paper coming to you soon in a favorite conference. But what we were able to achieve is that we were able to test 5 different AV implementations and generate scenarios for over 1,200 hours of wall clock time. Right. So again, the nice thing about Scenic is that it allows you to encapsulate the scenario difficulty in a compact form, and with that, we were able to use fuzzing on that on this language and do all this. Right. So I think I'm out of time, so I'll stop it here and enjoy the conference. Thank you.
Okay. Thank you, Sridhar. I think we have time for a couple of quick questions, if there are any.
Yeah.
So people on Zoom, feel free to unmute and ask. And those in the room, you can ask your question and I'll relay it again to Sridhar. Questions? Okay, well, I had one question, Sridhar. RSS example that you showed us, was it that the autonomous vehicle was programmed to follow RSS rules and you falsified it and you showed that, the so-called formal verification is not really quite done? Is that what happened there?
So we don't. Okay, there could be two things, right? So the RSS paper had pen and paper proofs on all of the correctness proofs, right? What we think has happened is that the translation of the rules from the paper into the implementation was not done properly. That is, someone who has implemented the RSS framework did not take into account the behavior of all the vehicles appropriately. And we believe that it's a mismatch in the translation from the specification to the implementation.
But also, I think the RSS paper, they did these manual proofs, but those are under certain assumptions, right?
Yeah.
And so I think one of the common things that I've seen is that the scenario actually violates those assumptions. And then you don't have guarantees anymore, right?
Yeah. I don't know if the scenario that we generated violates some of the assumptions, but from our understanding, it's the implementation mismatch between the theory and the actual implementation.
Okay. Great. If there's no more questions, thank you again, Sridhar.
Yeah. And, thank you.
Hope you can stay with us at least a little bit more. I know you might have to go and teach now.
Yeah, I just have to run to the class to teach.
Yeah. Okay. All right. Thanks for joining then.
Yeah. Thanks.
All right. So let's see. Next up is, so we're running 15 minutes late. So Kai-Chun, and you have shared the slides already with.
Yeah.
I think I might have it here. Yes. So I'll just project from my laptop. So Five minutes.
Hi, I'm Kai-Chun from UC Berkeley, and my presentation topic is dynamic and multi-objective specification and classification of cyber physical systems. And our preliminary results will appear in this year's Runtime Verification Conference. So let's start with this motivating example. So imagine that an autonomous vehicle driving on the road where there's here should be inland obstruction blocking the whole lane. Therefore, the ego vehicle must cross the center line to avoid collision with this obstruction. So from these examples, we can observe that multiple objectives could exist in the cyber physical system at the same time. Moreover, these objectives could conflict with each other. So in this case, the avoiding obstruction and obeying the traffic rules cannot be satisfied at the same time. So we must give them some priorities. For example, when the ego vehicle gets close to the inland obstruction, we want avoiding obstruction to have a higher priority so that the ego vehicle would not actually collide with the obstruction. And moreover, this priority could evolve over time. So when the ego vehicle is still very far away from the obstruction, we do not want it to cross the center line too early. We want it to stay in the original lane until it gets too close to the obstruction. So in the first segment, we would prioritize obeying traffic rules. And when the distance between the ego vehicle and the obstruction become less than a threshold, we give avoiding obstruction a higher value. And after it successfully avoid the obstruction, since there is no longer any obstruction, we can ignore this rule and make it become absolute. And we call this form of specification the dynamic rulebook. And given the scenario with this corresponding dynamic rulebook, we propose a falsification framework to generate counterexamples of the scenario. So due to time limitation, I'll just briefly go through our framework. So given the rulebook, we divide the scenario into several segments, and each segment would correspond to a fixed static rulebook. And then we create, for each static rulebook, we create a dedicated sampler for it. And during the falsification process, each sampler would focus on the corresponding segment of the scenario. And we also design an iterative falsification algorithm to generate samples iteratively. And we use, so in addition to the motivating example I just mentioned, we also design several scenarios in both autonomous vehicle and robotics domains. And we use Scenic to model these scenarios. And our falsification is also integrated with the Verify tool. And here's experimental results. So using our proposed dynamic rulebook specification, we can identify more counterexamples than using only a static rulebook, where the static rulebook means the priorities among objectives does not change over time. So our dynamic rulebook can better capture the dynamic nature of cyber-physical systems. Thank you.
Thank you. Well, on time, so we have time for a couple of questions. Yes,
yeah, questions. What is the priorities of the rule? Are those mentioned in the rule book, or they don't primarily understood? Like, for example, you had two rules. One is to obey the traffic and avoid collision.
Yeah.
When it happens, you have a higher priority for avoiding collision. How do you know that? Like, what it is given?
So let me just repeat the question for the Zoom audience. The question is, how do you determine the priorities and decide which one is more at a given point in time?
Yeah, so we currently assume that the dynamic rulebook is given before the falsification process.
That has the priority for all the rules?
Yeah, I mean, how to update the dynamic rulebook.
Okay.
We assume that, we have two settings in our work. So the basic setting is that the dynamic rulebook and as well as how to update it is given before the falsification process.
Okay.
And we also have another extension, which is we allow on-the-fly construction of the rulebook. So the rules may be added during the falsification process, and the priority may be different across different simulation iterations. So we have like two different kind of settings.
Right. Thank you, Kaichan. Next is Ryu.
So hi everyone, my name is Roy Song, and I'm a third-year PhD student at Purdue University Computer Science. And my research focuses on the autonomous vehicle security, the attack and defense against each component of the autonomous vehicle, like perception, planning, or recently like more popular end-to-end models. So my presentation is on discovering adversarial driving maneuvers against autonomous vehicles. So the goal of this project is how to identify how to attacker identify adversarial maneuvers that cause the autonomous vehicle to deviate from its mission while maintaining low liability. So to do this, we first extract 7 missions, different levels of AV to comply from the NHTSA document. So we use two matrix and categories to differentiate these missions. Let me give you an example here. We formalize them to the linear temporal logic formula. One of them is time to collision between the victim car or the AV and the front car to larger than the reaction time. This could be human reaction time if it's level 2, and it could also be the physical maximum brake time for the full autonomous driving cars. And the low liability here is we want to identify the adversarial maneuvers that cause the autonomous vehicle to deviate from mission. The low liability here means it should not crash with any object in the traffic, and it should not violate the traffic rules. So when the crash happens, when the autonomous vehicle crash, the law enforcement should not accuse the attacker for its responsibility. So after the attacker make the victim crash, we don't have any responsibility on that. Please cannot arrest me, something like that. And we represent this low liability with 7 LTL formulas. For example, the attacker should not make excessive maneuvers. It's very abstract here because we need more specific numbers to show this. Here it's like the throttle, brake, and steer value should less than threshold. This is what how we enforce it in Carla. Because in Carla it's the value between 0 and 1. We set threshold there, and we enforce that on the attacker. We are not going to generate any maneuvers that's larger than this value. Our threat model is that the attacker drive their own car near the victim vehicle to conduct the attack, and the attacker should have the knowledge of the victim car's control software and physical state, so it can generate the maneuvers beforehand and conduct it around the victim car. So here's one example. This is the attack on the open palette, which is level 2 driving software. It basically can do lane centering and car following. It seems the video is not.
Oh, maybe I don't have access to it, maybe.
Yeah, it's not. So.
Why don't you keep going and then time.
Yeah, if I have time, I will use my. So the system is called a Chilo. It's this is a system overview. So basically, we identify autonomous vehicle's mission. Like I said, the vehicle should maintain a time to collision with front car. We pass that to the simulator, and we generate a set of adversarial maneuvers. After we conduct it, we run a low liability check. If it's not violating, we do another research on the attack elements, and we guide this from the robustness of the victim car. Like if it makes the time to collision time reduce, we keep it. We generate another set. We verify whether the attacker violates the low liability check. If it's violating, we rewind to the previous state before we conduct that adversarial maneuvers. We repeat this process until we find we make the victim car violate its mission, or with success, and we find the right trajectory. Yeah. So do you have any questions?
Thank you. One quick question.
Oh, sorry.
I have a question about the purpose of the attacker. So, if you could imply what was the purpose, like what is the attacker doing to the victim vehicle again?
Yeah, so we're just driving around the victim vehicle. We can block the perceptions or trigger some doing some dangerous maneuvers to make it to make the victim car the autonomous vehicle bad decisions.
Would a practical purpose of this be like
So for example, if you know the victim part is using open patterns. So that video is actually pretty interesting. So I just drive. I noticed that it doesn't do really well in front of roundabouts. So I drive my car at front of it, stay for a specific amount of time, drive away. That car might get lost in that roundabout if you drive to the wrong direction or to the child.
I think we may have time at the end of the session.
Yeah.
So if you can connect to the Zoom meeting,
Oh, sure.
then just from your laptop, you can play it
Oh, yeah.
after we go through all the presentations.
Yes,
Right?
exactly.
Okay. Actually, let's continue that discussion later. Okay.
Okay, sure.
My take. Slides show here. Those of you who have uploaded slides, is that fine?
Yeah.
Okay, great. And if you have embedded video that should play, make sure that you give me access. So sasia@berkeley.edu.
Hi everyone, I'm Heidi from Vanderbilt University. So I will give a brief introduction about what I have done in the past 3 years with my PhD.
Sorry to interrupt. It's just that I don't know if it's just me. I don't see the slides.
Sorry, if you want to share screen.
Thank you.
Thanks so much for picking that up.
Yeah, so as we know, the canonical
Okay, I think it's the connector to the
canonical model for capturing sequential distributed process is MDP, but for the autonomous, should I change the?
Does the screen look okay, or is
Yes,
multiple?
I think it's due to animation, or I can just use it.
No, this is okay.
Okay.
Is that the right slide?
Yeah, yeah.
Okay.
This one. Okay,
Okay.
So as we know, the autonomous CPS normally operate in the highly dynamic environment. So this environment may change with the time. That means, for example, if we model the environment as MDP, the dynamic, the transition function or the reward function for some applications may change with the time. So this may raise two questions. The first question is how can we make the decision makers explore the environment first and then to gradually adapt to the new environment? And the second question is how can we make the leverage the prior knowledge to help with the decision making for the current decision environment. And this is the first work we proposed. It's called the dynamic syntax. The high level idea for this work is that we want the decision maker to switch between the two controllers. One could be the SIP controller, which narrates the SIP policy, and another controller called the performance controller. It's a black box controller. So the policy for this controller could be performance driven, and which means it can be used to it is used to optimize the expected return. And basically, we let the two types of controller run around the city. So we propose our own scenario generation tools and to collect the data and to create the Q value function for these two different controllers, and then use the decision making algorithm to make the agent look into the future to decide, okay, if it's safe to switch back to the performance controller, and if it's should we switch to the SIP controller now? And this is the demo video for how this works in on a simulator. It cannot be played, but I can play it after if someone is interested. But for the previous work, we didn't consider how to do online adaptation. So we proposed this work called the actor as user. The idea for this work is that we do risk-averse strategy at first to make the agent explore the environment simply to collect the data, and then we transfer the knowledge from the previous model to the current model, and use the collected data to fine tune the current model. And this part shows that so if the agent is very confident about what will be happening after taking the action, it will take the strategy to optimize the expected return. And if it's not very confident about what will be happening, then it will take the worst case sampling strategy. This should be an animation plan. Yeah. And so let's say if we have already updated our model, but we know that if we want to do any online decision making, this online decision making always normally takes time. So how can we leverage the prior knowledge to speed up the conversion of the current decision making process? So we basically prove that leveraging the Q-value function from the previous environment and combining with the model we have on the head to make the decision can speed up the emergency of the online decision making procedure. And this is a very high level description about what we have done. And if you are interested in the details of this different works, please feel free to talk with me, and I'll be happy to share the details. Thank you.
Thank you, Baiti. Questions? So for these last two works that you presented, are these techniques for modeling agents in a testing scenario? Is that a use case that you're considered, or?
Yes. So we basically say so it would be similar to MPC model predictive control, but it's slightly different. That is, we stay with.
I see. It's more for control as opposed to for test generation.
Yeah.
Thank you. All right. Next, Aaron.
Yeah.
And your slides are in here too? No?
So do you CK can share your screen?
Is CK there?
Yeah, hi guys. I'm remotely here. So Aaron is our simulation team representative from the racing team.
Right.
So he's going to be coming up in front, and I think we're going to hand this off back and forth here just because I might have to be called away to track.
Can you share your screen, CK?
Let me see here. Can you guys see? Hold on one second. Can you?
It's coming up. Yeah.
We can see it.
We can see.
Okay, sounds good. So I'm gonna let Aaron introduce our team. I'll introduce myself real quickly. I'm a former technical program manager at Berkeley. I did my master's at Berkeley, and I'm an incoming PhD student. I work as the simulation team lead for the autonomous racing group, AI Racing Tech. That's a multi-university collaboration team, and we're looking at using Scenic in some of our testing and toolchain applications. And I'm going to hand it to Aaron to kind of intro this, and then he'll hand it back whenever he's ready. Aaron, you can go ahead.
Aaron, can you stand over here? Because the microphone is...
Okay. Yeah. Hey, everyone. My name is Aaron. I'm a rising second-year undergrad student at UC Berkeley. I've been in AI Racing Tech for quite a bit now, I think almost 2 years. I've just worked on some of those side projects now and then while balancing with academic school workload. So this is kind of a marketing program we had a couple of while back. I think this was back when our vehicle becomes, actually no, this is a new one. So our vehicle is the blue and gold. It kind of represents Berkeley. and more stylish fashion. And yeah, I guess to talk about our team, we're an intercollegiate racing team. It was originally started by University of Maui at Hawaii, and then to kind of get more talent and like minds to work on it, we've expanded to UC Berkeley, UC San Diego, and Carnegie Mellon. And I believe that's it. That's listed up here. Yes, those ones. Okay. I guess we can move on to the next slide.
Okay. This is a promo video, Aaron. Just a heads up. Do you want me to skip this, or do you want me to go ahead and play it?
The next one.
Mm-hmm.
I think we've already seen the promo video, so
Yeah.
we can move on.
Okay, let's go ahead.
So right now we're going to race in September 6th. So this is kind of like the schedule we had leading up to it. In the beginning, it was in July. Our on-site team did some research work at EMC2, which is the warehouse that stores our car. And then throughout July and August, we just mainly tested our vehicle in the Speedway. And then we did occasional testing in the 84 Speedway, which is where the competition would actually be. We're kind of like in the final stretch now, late August. In the end, we'll race in the 84 Speedway once more. I think this time around, the IC Challenge is going to hold like a rather big conference, bigger than before. It's going to be like lots of university students and businesses who are interested in autonomous racing development and more. Right. And so here's the rule set for
Again, if you can stand here, it's best.
I got it. So here's the rules for this kind of race. You can think of it as like a F1 race, although we have specific rules. So the first one, phase one, is we just go for pure speed. So which car can go? It's so small. There's some more information. Phase two is head to head. So this is what has been done past. There are two cars. Hopefully those are like
The promo video had it.
yeah. So this is when we start at like some base speed, and then each car passes one other, and then so like let's say we start at 100 kilometers per hour, and then so we have two cars. The first car has to pass it, and then the next car must pass it as well. So then both cars are gonna pass the 100 kilometers per hour mark. After that, we increase to the first day like 10 kilometers. I think they use miles because we're in America, but yeah. And then for the last phase, this is new. This is rather ambitious. I'm not sure how well this will go, but this is when we have, instead of just two cars running head to head, we have multiple cars. So this is kind of, I think the goal of this is kind of push more towards actual F1 racing, where if you've seen like on television, there's like many NASCAR vehicles just racing together. Yeah. We move on.
Okay.
Next slide.
Okay, so this is like what we're doing right now. This must be like some updates. For some tracks that are, I guess I'll pass it off to CK now.
Okay. So currently, the reason why I'm remote for this session, we were really looking forward to attending it, but we're actually trackside right now prepping for the competition that we have on September 6th. I think that Aaron mentioned the rule set for. So this is just a little bit of background for what we're doing on track testing, for kind of informing what we're looking at doing with Scenic and kind of in the loop with validation. On track, when we're physically on track, we do a lot of telemetry published ghost cars or telemetry published obstacles on track. So we're practicing trying to avoid obstacles at speed or trying to avoid online agents who have some strategic decision making, so that we're doing this testing before we get to the multi-car testing. In addition to this, we do a ton of data collection, and a lot of that goes back into the loop and informs how we're generating these policies, and how we're looking at how we're training our controls algorithms, our perception algorithms, and everything in the loop with data is incredibly important for everything that we do. So I'm tempted to hand it back to Aaron, but I think for the sake of time, I might hop through these, Aaron, and then I'll tag you in here and there. So from a high level, the sim theory challenges that we face on our side, we look at vehicle modeling. So we're trying to model things out of the drivetrain, the suspension, the dynamics, and looking at aero modeling as well. The sensor fidelity differences are a big problem for us when it comes to the GPS, camera, LiDAR, and radar. And we want to be able to sort of test these edge cases in sim. We also care about low-level fault modeling. So a lot of this kind of informs how well we can do our simulation modeling, test our agents, and deploy them in the real world, because we're really looking at performance at the limits and what we're doing. So I'll let Aaron go ahead and do a little bit of a summary for this one, and then Aaron, you can hand it back to me whenever you're ready here.
2 minutes, please. 2 minutes. Okay. So for seeing our racing stack, we use both low fidelity and accuracy simulations. For low fidelity, we use AutoVersa as our physics engine, along with Arvid and Foxglove for visualization. This kind of like helps us do behavior planning, because it's not that well defined, but helps us get a general idea of how our model is behaving on the system. Okay. Next slide, please. Here's a high fidelity simulation. We're using SVL right now, and this is when we think Scenic and Verify could come in very handy. So this is what SVL, our custom SVL, typically OSSDC, looks like. We want to have our EU agent, which is, I believe, this one, along with adversarial agents like that one. And we want to model this with Scenic. They also want to use Verify to kind of see like which scenarios where our driving is dangerous.
Okay, I'll go ahead and jump in, I think, at the end here. I just want to add a couple other things. So we are currently using SVL. In the future, we're looking to transition to BeamNG. We maintain kind of our own backend vehicle model and our own server because a lot of the interfacing just took a while to develop. So we kind of have been slow to switch out. But we're hoping to look at wrapping in Scenic and Verify to have more testing of the edge cases of what we're doing in simulation and better modeling of non-ego agents. So on our side, the way that we're currently testing is we do version control for our racing stack through Docker. So we're able to push and deploy different copies of our racing stack through the Docker Hub. We have a config file that will tell you sort of what is going to launch with the actual racing stack that's Dockerized. And we have a SimCI workflow with our sim runner, where currently on the testing side, we're really doing just purely end-to-end. A lot of things where we're doing a full race scenario and racing 2 cars and our stack against itself in order to try to do this testing and validation. We collect the ROS bags and we sort of manually process a lot of these ROS bags in the different subteams. So we're looking at kind of this early wrapping in Scenic and Verify for better falsification to have higher test coverage and more safety scenarios modeled. So I think this is a really interesting opportunity in this format. And if there's students, I think, in this group who are interested in sort of cross-collaborating or have suggestions or ideas for us and how to model this, or just questions in general, we're very interested in the cross-collaboration piece.
Okay.
Yep.
I think we should wrap up here. Thank you.
Yeah. No problem. Thank you.
All right. So let me see. I think Chris is on the list to present. Let me double check the schedule here. This is up next. So, sorry, I can't try to eliminate that bar.
No worries, no worries.
Strange things happen with Zoom.
All right, thanks everybody. My name is Chris Miller. I have a local software development company. I love the racing thing that we just looked at because what got me into machine learning in the first place was AWS started a racing league with a toy car, and the object was to train the car to drive around a track. And so my first experience was with reinforcement learning. And that kind of set me down this pathway, my machine learning journey. I'm also part of a developer group called the AWS Heroes. They recruited me into that group, and it's just been a great opportunity to collaborate and learn from others within the AWS ecosystem, which is giant. So I was able to present on this project at AWS reInvent in 2021. And one day I was sitting in traffic here in Santa Cruz, and I thought, I wonder if reinforcement learning could be used to improve the traffic congestion, right? Anybody in Silicon Valley or really anyone has experienced this. And I found an academic paper that suggested that you could get a 16% improvement in traffic flow. So I launched an internal R&D project. I worked with the data scientists that used to work with us, as well as some interns of the UCSD to work on various parts of that project. And so this is the technology that currently controls most of our traffic lights. It's literally from the 1990s. It might even run Windows XP. It's really antiquated. It uses a bunch of analog sensors. This is a wire loop that just detects the presence of a heavy vehicle in the street. There are some radar sensors and some other types of slightly more advanced sensors that we use, but really it's past time for an upgrade. So the system that I envisioned uses computer vision. It has a model that's hosted in the cloud that inferences and provides all of the decisions for the traffic street light controls. And then I'm looking at an IoT controller that can interface with the existing systems to keep costs down, so we don't have to replace what's there. We can just augment it. And then if the system goes down, this old antiquated technology is actually really good at kind of fail-safe scenarios. All right, so Google currently has a project that they are testing out in one municipality, I believe. And I believe what they're doing is they're using the data from our phones. We all have Google Maps. Our phones are being tracked, and that gives a representation of traffic congestion. Personally, I feel like that isn't granular enough. And if we were to install cameras in each of the traffic intersections, we would get a lot more rich data, not just the number of cars that are on the road, but we could start to look at things like acceleration profiles. Like if there's a Mustang and a semi-truck side by side at a light, I guarantee the Mustang's going to get to the next light faster than the semi-truck. So it's not just necessarily about types of vehicles. With computer vision, we can say not only is it a sedan, but it's a sedan that has a four-cylinder. We know that model is going to have a slower acceleration profile than one that maybe uses a V8 in it, for example. Okay, so this, if it's I guess the GIF didn't transfer over, but this is the Sumo system for representing the traffic. And so where we're at this point is we have a computer algorithm that runs in the cloud that will make the decisions, and that would be represented here on this GIF. We've developed the camera technology, but what we've learned is that to keep costs down, we would prefer to put one camera at an intersection instead of multiple cameras, because with multiple cameras, you also run into an issue of having to deduplicate data as the same car is picked up by multiple cameras. So we can use a camera that's pointing straight at the ground with a fisheye lens and get a 360-degree view of the intersection. Let's see, one of the problems that we run into with that is all of the computer models that are able to detect cars, like the yellow series of models, they're trained on data looking at the side of the vehicle, whereas we're going to be looking from the top down. And those models just don't recognize the object. So we need to train a model. That's where Scenic comes in. I'm totally new to Scenic, but I see opportunity here to be able to generate synthetic data that we need to generate a basic model that I believe would be good enough for us to use as like an auto labeling model. So we can take real world video from intersections, use a synthetic model to auto label. And again, not only just is it a semi truck, is it a sedan, we might be able to through the different car models and Scenic get down to like brands of vehicles, maybe models, So I'm not sure how well it'll work until we do it, but that's my initial interest in Scenic. And then, as we discussed yesterday at the reception, I think there's an opportunity to use Scenic and Carla as a real world representation of real-time traffic patterns, or being able to rewind and go back and look at previous traffic congestion issues. And, in a bird's eye view, municipal, like a city planner, would be able to go to any particular area in their municipality and to be able to witness like what was really going on that caused the traffic congestion. Whereas today we're limited to Google Maps that just have a red line. Like, we know it was slow, but we don't know why. We don't know what kind of vehicles were at the intersection. And so I think there's a great opportunity for that as well. Thank you.
Okay, thank you. Questions for Chris? In the room or online? Okay.
Yeah.
Two questions. Okay, Anirban.
Yeah. So is there any particular benchmark that we are looking at for the traffic? Like if you have cameras there that collect video of others driving around the traffic.
No, again, this was based off some research. There's an academic paper that suggested that we can see up to a 16% improvement in traffic. This was mainly an R&D project internally. It was an opportunity to build a really complex system that uses different parts of the AI ecosystem. I'd love to productize it. There's a chance we may open source it. We're sort of trying to make the decision of how we move forward with this. So to be able to collect traffic data, we did do a test where we hoisted a camera up on a 16-foot 2x4 at an intersection. We didn't ask for permission. So in order to really collect the data we would need authorization from the municipality to mount one of our cameras on an intersection on a light pole to be able to collect that data.
Yeah.
You've been looking at the intersection data, right? Have you ever considered to use it for parking lots? So those are also kind of community private.
Yeah, actually, I do have some experience. We have a customer that is in the security sector. And so there are computer vision solutions on the market, access cameras. There's a vendor that provides some object detection layers in there. And I understand that this technology can be used for like enforcing parking time limits. So you can track the individual vehicles, and if you have like a 3-hour parking limit, that technology can call out to the local person who's enforcing the parking to go cite those vehicles for extending their stay. Does that answer your question?
Yes, I have something else in mind for this top 5.
Okay, sounds good. All right, thank you, everyone.
Thank you, Chris. All right, so we had time for discussion that has evaporated, but the good news is we have working group sessions in the afternoon, and one of those will be autonomous driving. So I propose that we take our questions and thoughts and ideas from the session and launch the discussion in the afternoon.